For the first time in human history, we know there is a planet orbiting the closest star to our own. Not just any planet. A rocky world, roughly the size of Earth, sitting in the habitable zone where liquid water could exist. Proxima Centauri b sits just 4.2 light-years from Earth, close enough that if we ever built a probe capable of reaching 1/5 the speed of light, we could send back images within our lifetimes. This should be the greatest discovery in the history of astronomy. A next-door neighbor, a world we could study, perhaps even visit. But I need you to understand something before you get too hopeful. Proxima b orbits its star every 11 days at a distance over 20 times closer than Earth is to the Sun. And that proximity is the beginning of every single problem this planet faces. Because while Proxima Centauri may be our nearest stellar neighbor, it is also something far more dangerous. A weapon, a planetary atmosphere destroyer, a world-killing radiation furnace masquerading as a dim red star. Let me walk you through what we know, and by the end, you'll understand why salvation and disaster are not two different outcomes for this planet. They are the same outcome viewed from different angles. Proxima b currently receives 30 times more extreme UV radiation than Earth and 250 times more X-rays. That alone would make survival difficult. But the real nightmare isn't the baseline radiation. It's what happens when the star gets angry. Proxima Centauri has a hair-trigger temper, erupting with giant flares every day, and medium to small flares many times per day. And these are not solar flares like the ones our sun produces. These flares are around 100 times more powerful than anything our solar system experiences. They don't just heat the planet. They strip away its atmosphere molecule by molecule. In 2017, astronomers observed one of the largest flares ever recorded from Proxima Centauri. The flare boosted the star's brightness by a factor of 1,000 over a 10-second span. Imagine standing on the surface of Proxima b at that moment. The sky would have gone from dim twilight red to blinding white in less time than it takes to blink. A flare 10 times larger than a major solar flare would blast Proxima b with 4,000 times more radiation than Earth gets from solar flares. And this is not a once-in-a-lifetime event. In 2016, Proxima Centauri flared so violently it became nearly 100 times brighter, just visible to the naked eye, and statistics suggest such super flares occur around 5 times a year. The problem isn't just the intensity, it's the repetition. Flares like these have been happening for billions of years. Over the billions of years since Proxima b formed, flares like this could have evaporated any atmosphere or ocean and sterilized the surface. Even if the planet started with a thick protective blanket of gas, the radiation doesn't stop until there's nothing left to strip away. But let's assume for a moment that Proxima b somehow retained an atmosphere. Maybe it had a massive water inventory at formation. Maybe volcanic outgassing constantly replenishes lost gases. Let's be optimistic. Even in that scenario, the planet faces a second existential threat: tidal locking. Proxima b is likely tidally locked to its star, meaning one side of the planet permanently faces Proxima Centauri, while the other side remains in eternal darkness. This is the same reason we only ever see one face of the moon. When you orbit that close to a star, gravity locks your rotation. What does that mean for the surface? A 1-to-1 tidal lock would lead to an extreme climate with only part of the planet habitable. The day side would be scorched by constant radiation. Temperatures could climb to several hundred degrees Celsius. The night side would be frozen solid, potentially colder than anywhere on Earth. The hot side would permanently face the star, while the opposite side remains in permanent darkness and freezing cold. Between these two extremes lies the terminator, the narrow twilight band, where day meets night. Any habitable areas would be confined to the border region between the two extremes, referred to as the terminator line, since it is only here that temperatures might be suitable for liquid water to exist. But habitability on the terminator depends entirely on whether the planet has a thick enough atmosphere to redistribute heat. On a tidally locked planet with sufficient surface water, liquid water could be present at least in the substellar region, but this requires minimum greenhouse warming such as 10 millibars of carbon dioxide and 1 bar of nitrogen. Without that atmosphere, there is no heat transport. Without heat transport, there is no habitable zone, just two uninhabitable extremes separated by a thin strip that may or may not support liquid water, depending on factors we cannot yet measure. And here's where it gets worse. Because Proxima b is in the habitable zone, it's so close to the star that it's tidally locked, and without rotation, it can't generate a protective magnetosphere. Earth's magnetic field deflects the worst of the sun's radiation, funneling charged particles toward the poles, where they create auroras instead of stripping away the atmosphere. Proxima b doesn't have that protection. The planet is likely laid bare to radiation, and without a protective shield combined with exposure to intense stellar radiation and frequent flares, it would be surprising if Proxima b could maintain an atmosphere, let alone be habitable. NASA ran simulations to model exactly what would happen to an Earth-like atmosphere in Proxima b's orbit. The model shows Proxima Centauri's powerful radiation drains an Earth-like atmosphere as much as 10,000 times faster than what happens at Earth. Even in the best-case scenario, assuming a closed magnetic field and the lowest thermosphere temperatures, Proxima b could lose an amount equal to the entirety of Earth's atmosphere in 100 million years. And with the highest temperatures and a completely open magnetic field, that same loss would occur in just a fraction of the time. To put that in perspective, complex life on Earth took over 3 billion years to evolve. Proxima b's atmosphere, if it ever had one, may have been completely eroded before life had a chance to even begin. One astrophysicist concluded that Proxima b's atmospheric loss rates are so high that habitability is implausible, raising questions about the habitability of planets around red dwarfs in general. And Proxima Centauri is not unique. It is a red dwarf, the most common type of star in the galaxy. Red dwarfs are the smallest, coolest, and most common type of star, with estimates ranging from 70% to more than 90% of all stars. Most exoplanets we discover orbit red dwarfs. If these systems are inhospitable, then potentially habitable real estate in the universe just became catastrophically scarce. It may turn out that most red dwarfs are hostile to life, and in that case, planets around more massive stars like our Sun might be the optimal location to search for inhabited worlds. But let me be honest with you about something. We don't actually know if Proxima b is dead. We don't know if it has an atmosphere. We don't know if it has water. We don't know its exact mass, its composition, or whether it has a magnetic field. Everything I've told you so far is based on models, simulations, and educated guesses built from fragments of radial velocity data. Proxima B's properties are only poorly understood, but it is probably a terrestrial planet with a minimum mass of 1.06 Earth masses, and it is not known whether it has an atmosphere, which would impact habitability. The planet doesn't transit in front of its star, from our perspective, so we can't use the standard method of analyzing its atmosphere by watching starlight filter through it. We're flying blind. And that's what makes this so maddening. The closest potentially habitable planet to Earth is also one of the hardest to study. Still, some researchers refuse to give up on Proxima b. Recent work concludes that Proxima b is a viable candidate habitable planet. Climate models show that under certain conditions, liquid water could exist. A broad range of atmospheric compositions can allow surface liquid water. And on a tidally locked planet with a surface water inventory larger than 0.6 Earth oceans, liquid water is always present, at least in the substellar region. An ocean-covered Proxima b could have a much broader area of surface liquid water, but at much colder temperatures than previously suggested due to ocean heat transport and depression of the freezing point by salinity. If the planet's ocean is highly saline, freezing temperatures drop significantly. Heat circulation through ocean currents could extend habitable regions far beyond the substellar point, possibly even into the night side. For an evolutionary path leading to a highly saline ocean, Proxima b could conceivably be an inhabited, mostly open ocean planet dominated by halophilic life, organisms adapted to extreme salt concentrations. And there's another possibility. Experiments show that when microorganisms receive very high fluences of ultraviolet radiation, such as those expected during flares, a fraction of the population is able to survive. Life could cope with highly UV-irradiated environments in exoplanets under conditions that cannot be found on Earth. Maybe life on Proxima b, if it exists, is nothing like us. Maybe it evolved in caves, in subsurface oceans, or around hydrothermal vents. Maybe it developed defenses we can't imagine, biochemical shields against radiation that would instantly kill anything on Earth. Or maybe it never got the chance. Here's the thing that keeps me up at night. Red dwarfs have an extended pre-main sequence phase, and their habitable zones would have been in a region where water was gaseous for around 1 billion years, subjecting terrestrial planets to a runaway greenhouse effect that would allow hydrogen escape to space and the loss of several Earth oceans of water. Proxima Centauri's habitable zone was farther away early in the system's existence, and assuming Proxima b formed in its current orbit, it could have spent up to 180 million years too close to its star for water to condense, suffering a runaway greenhouse effect where water evaporated into steam, was split by UV radiation, and the hydrogen escaped. Even if Proxima b started with oceans, it may have lost them before it ever cooled down enough to be habitable. And once the water is gone, it doesn't come back. But I want you to consider one final possibility. What if we're asking the wrong question? What if habitability isn't binary? What if Proxima b represents something we've never encountered before? A world that straddles the line between hostile and habitable, depending on where you are and when you look, depending on properties such as tidal locking and amounts of water and carbon dioxide. Scenarios include a planet partially or wholly covered with ice, planet-wide or small oceans. Combinations of these, scenarios with one or two eyeball-shaped areas of liquid water, or a subsurface ocean with a thin ice cover. Proxima b could be an ice world with scattered oases. It could be a desert planet with underground aquifers. It could be an ocean world with a single habitable zone directly beneath the star. We don't know. And that uncertainty is the most terrifying part, because future large telescopes, such as the James Webb Space Telescope, could directly observe Proxima b, and possible observable traits include the reflection of starlight from an ocean, radiative patterns of atmospheric gases, and hazes. Within the next decade, we may finally get answers. If Proxima b has an atmosphere, we'll see absorption lines from water vapor, oxygen, carbon dioxide. If it has oceans, we might detect a glint, a reflection of starlight bouncing off liquid water. If it's dead, we'll see nothing but bare rock or ice. And here's what makes this discovery so significant. Proxima b is not just a planet, it's a test case. Arguments concerning the habitability of red dwarf systems are unresolved and remain an open question, with observational data suggesting uninhabitability while climate models favor habitability. If Proxima b is habitable, then potentially billions of planets around red dwarfs across the galaxy could support life. If it's dead, then the universe is far emptier than we hoped. Our sun is expected to burn out in about 4 billion years, but Proxima Centauri has a much better forecast, perhaps burning for 4 trillion years longer. And if Proxima b is habitable, it might be an ideal place for humanity to move, possibly a future home. But if it's not habitable, if the flares have already sterilized the surface, if the atmosphere is gone, if the water has been stripped away into space, then Proxima b becomes something else entirely. A warning, a reminder that being in the habitable zone is not enough, that proximity to a star matters, that stellar violence can erase habitability no matter how perfect the conditions seem on paper. Proxima b is teaching us something whether we find life or not, showing us the diversity of planetary environments, the resilience required for habitability, and the importance of magnetic fields and atmospheric retention. So, when you hear about Proxima Centauri b, the closest exoplanet to Earth, the world that could theoretically support life, the planet that sits in the habitable zone of the nearest star to our sun, I want you to remember this. Proximity is not the same as safety. Being close doesn't mean being survivable, and the universe does not owe us a neighbor. Proxima b is 4.2 light years away, close enough to dream about, far enough that we may never know the truth until we go there. And when we do, we might find a world teeming with life adapted to conditions we never imagined. Or we might find a graveyard, a planet that almost made it, a world that could have been home. Either way, it will tell us more about our place in the universe than anything we've discovered so far. Because Proxima b is not just our closest neighbor. It's the first real answer to a question we've been asking since we looked up at the stars. Are we alone? And if we're not, what does it take to survive?